Continuing in our discussion about covariates, let's talk about spurious relationships. The relationship of x1 to y might have nothing to do with x1 influencing y, but rather the relationship itself exists because of another variable, say x2. In this case, x2 is called a confounding variable. Here's an example. Age can influence both height and math achievement. So while it might look as though height is causing math achievement, it's not actually height. It's actually the developmental processes associated with age. Height is one of those, and so is the ability to reason through the mathematics problems that become more and more difficult with higher and higher grade levels. So if we were going to symbolize this, that is going beyond the symbolism that I showed and referring to the symbols that I talked about earlier in the last video. So we have here age, we have height, and we have math ability or math achievement. And what we notice is that these are correlated, and the question becomes, okay, they covary. Is one of them causing the other? The answer to that is no. Age is actually creating the relationship for both of them. Now, what you can sometimes have is a mild relationship. Let me use something besides height and math here. Let's just make it generic. So we could have a mild relationship, and we'll talk a little bit more about this when we talk about both direct and indirect effects. We could have, I'll just put in a dotted line to indicate there that maybe there is something going on in terms of a direct relationship, but most of it is just a correlation that's caused by this second variable. In other words, the fact that this second variable is causing the correlation doesn't mean that if we wipe out this second variable, that will automatically wipe out everything. There might be something a little bit going on between these. Trying to get the eraser there. There we go. There might be something going on that's a little bit weaker in nature here than what we saw when we had the other two variables, or the second variable, x variable, influencing both of those. So let me exemplify this with some R work to show you how we could look for this kind of spurious relationship, which could mean another variable accounts for all or most of the relationship. Let's take a look at that with an example using some actual data and using R. So I'm using the high school and beyond data. And so let me go ahead and load that data. And so now here in my environment, which let me clear it and try it again. Okay, now we can see that we have these data from 200 observations of 11 variables from high school seniors collected by the National Center for Educational Statistics. And let's look at the amount of variation in science scores that is accounted for by math scores. So math is viewed as an important skill for proficiency in science. So using our new language about this, I am going to regress science on math. And regressing science on math, here's what we get. We find out that the R squared is about 0.40, meaning that 40% of the variation in science scores could be thought of as associated with and perhaps even affected by, perhaps even caused by the variation in math. So having variation in math ability could cause a variation in science ability because of mathematical knowledge being a prerequisite for much of what one does in science. Remember, this is at the high school level. Okay, so think about this, however, especially if you're taking an achievement test. Might it not be possible that reading influences both math and science proficiency measures, given that this is a written test and reading and interpreting the test items correctly is a first step in obtaining a successful outcome with that item? So let's take a look. So a confounding variable, as I say here at the top, influences both an explanatory variable and the response variable and accounts for some or maybe all of the relationship we observe among these variables. So I'm wondering, is the relationship between math and science somewhat spurious, completely spurious? Is reading a potential confounding variable? So let's look at how we would actually approach this problem. First of all, I'm going to go ahead and see if reading is associated with both science and math, both the explanatory variable math and the response variable science. Because if it is not associated with both of those, then it cannot be a confounding variable. So let's see if it's associated with both of those. So the first one I did up here was science, and what we found is indeed 40% of the variation in science scores is associated with reading scores. And down here for mathematics, it's even a little higher. 44% of the variation in math scores is associated with science scores. So what we can do is the following. So when we created these models, one of the things that you get out of these models, if we look over here at model 2, which was reading and science, one of the things you get out of these models are the residuals. Let me actually go ahead and type it over here in the console. And in the console, this is called model 2. And so I'm going to ask for the residuals, and you see that we get 200 residuals. Well, what are residuals? Let's go back and look at our diagram again. Let's create a new diagram here. And so if we have X that we think is influencing Y, that there could be things that are not in our model. These are the errors. And error just means that it's an error of your model, meaning there's things that are not in the model. So when we look at residual, we have already taken out any of the influence of the X variable. So if I'm looking at the residual for, in our particular example, let's call it back up here. If I'm looking at the residual after regressing science on reading, I'm looking to see what other things there are other than reading. That is, reading has already been removed. Similarly, in Model 3, we looked at reading and looking at math. Math regressed on reading, reading predicting math. And so the residuals for that would be other things that influence the mathematics score besides reading. So note, if we combine these two ideas, is that, and I did not mean by combining those two ideas to literally move the line, but I did. If we combine the two ideas here, then we're looking to see, when we look at the residuals, reading removed from science, reading removed from mathematics. So now what I'm doing down here on line 35 is I'm correlating the residuals from the two models. So I have those two models. Let's go back here to the picture. So I have the two models. I have to see how reading influences science, and I see how reading influences math. And then I have, in one of the models, I have some error, and in the other model, I have some error. And now I'm looking to correlate these. I'm looking to see what the correlation's like. And what would that mean? That would mean the correlation of science to math above and beyond what reading is able to explain. And if reading is not a confounding variable, then we would expect the correlation of science and math to be very similar to what we found when we initially looked way back up here. We found that the multiple r squared was 0.40. So 40% of the variation in science was related to mathematics. So here I'm going to do the correlation, then I'm going to do a correlation squared, which is my coefficient of determination, which tells me how much of the relationship in one variable could be attributed to the other or explained by or vary with the other variable. And when I do this, look what I get. I get an r squared of 0.13. We dropped all the way from up here having 40% of the relationship, the variation in science accounted for or explained by the relationship in math, to now when you take reading out, 13% of the relationship in science is related to math. So there is this variable, this confounding variable, that is making the relationship look larger than it actually is. Now, are we back to first principles? Have we done deep enough? Many would argue no. Many would say, well, wait a minute. Reading, math, science, they all fall under this intelligence umbrella. And in fact, the original Binet IQ test operated under the assumption that there was this general intelligence. And there have been many psychologists over the years that have studied this idea of general intelligence. So maybe there's a general intelligence that is influencing everything. My point here is that when you look at these models, these are your theoretical models. These are the things that one comes up with based upon their understanding of what it is they're exploring. So if you want to get to first principles way back here before reading, what is it that influences all of this? You can do so. But in terms of what we have in hand right now, which is the reading scores, the math scores, the science scores, then I created this little idea that math should be required for science, reading should be required for both of them in terms of the ability to read, to be able to take the test in science and math. And indeed, I actually was a little bit surprised at how much reading dropped the relationship between science and math from 40% overlap in the variation to a mere 13% overlap in the variation. So to summarize, how do we go around about looking for a confounding variable? Well, when we note a relationship between two variables and we're suspicious of a third confounding variable, then what we do is we regress each of the individual variables on that potential confounder. And by so doing, we're removing the confounding, and then we go back to our original variables by correlating the residuals to find out what kind of relationship there is.